there, everybody. Welcome to the inaugural episode of Live Lab Days, sponsored by the Marine Sciences program at Stockton University. I'm Dr. Susanne Moskalski, Associate Professor of Marine Science and affiliated with the Geology program as well. The camera person for today is Elizabeth Zimmerman, a Senior Research Scientist at Stockton's Marine Field Station. For those of you who may be watching who don't know Stockton, we are located on the southern coast of New Jersey, very close to Atlantic City. And one of the things that's great about this location for a marine science program is proximity to the coast. So today, I am here to talk to you about salt marshes. We are here standing in a lovely, wide expanse of salt marsh that is, I don't know, it took us about 5 minutes to get here on a boat. So we're very close to Stockton. And this sort of salt marsh, this ecosystem is found all up and down the east coast of the United States. And there are, of course, regional variability in exactly what you see, but this is what we have around here. So the whole point of this program is to talk to you about salt marshes, and because I'm a sedimentologist, I study sediment for a living, that's my focus. So my focus is to talk to you, to explain how sediment works on the salt marsh. But, right, so I have an agenda. I have a very, very loose agenda of what I want to talk about, but I'm more interested in answering you guys' questions. So, if you have a question, please type it in, and Liz will read the questions off to me. All right, so do not be shy of asking something that's not directly sediment related. Right? If I don't know the answer, I will just tell you that. But I will do my best to answer any questions you might have. Okay? So, we don't want to get skin cancer, so I'll put the hat back on. All right? Now, we chose this particular spot because in close proximity, without having to really go very far, there's features on the salt marsh that when I see this salt marsh, when I see these features, I've got a pretty good idea about what's going on. So I can tell you a lot and describe a lot of processes and mechanisms without having to bore you by walking and having you just watch me walk. Okay? So I want to start with the thing that's most obvious. What do we see? What do we see? We see plants, right? There's plants all over the place, and it's mostly variations on grass with maybe a bush or two. Okay? But if we take a good look at these plants, right, there's different, you can see different styles of plant. This stuff in the front here that you're seeing right now is called Spartina patens. It's very, very skinny blades of grass. I think it looks kind of like hair. And you can see this year's lush green growth popping up through last year's growth. Right? The above ground biomass dies, makes a mat. And then the new grass will come up through it. So this is a Spartina patens. I want to say this is what they used to call salt hay, but I'm not 100% sure. Now over here a little bit to the right is a type of grass. You can see it's a little bit taller. The stems, individual blades of grass, are wider. And this stuff is called Spartina alterniflora. It also has a bunch of last year's biomass, and the new stems are growing up, right? Same general idea, but this is and it's the same genus, it's Spartina, but it's a different species. And this is cordgrass, and that's the other name for it, cordgrass. So this is different. And now you'll notice that there is a definite, they're all grouped together, all right? We've got a definite boundary. We've got a bunch of Spartina alterniflora here, and then really quickly, over maybe a foot or two, now it grades into completely Spartina patens. And on the interior here, it's almost entirely Spartina patens in terms of the grass. Another thing that we can see since we're going this direction, you see these tall stems here. These tall stems are from last year, and what these have is, bad news, invasive, these are invasive Phragmites australis. Now, the Phragmites can grow in a mighty big, giant stand and outcompete everything, because on the East Coast it's invasive. Right now there's over here, we can see some of them to the left, and we can see some of them back behind me are these bushes. These are marsh elder, right? As we've got this area of bushes here, and right along the riverbank, there is more tall stems, right? Those are probably 3-ish feet high. Those are not the frag, those are Spartina sinusoides. And it's, again, Spartina, but it's a different species. So what we're seeing here as we look around the marsh and pay attention to the grass, we can see, and the plants, is that we can see that there are multiple species of plant, and they tend to grow together, you know, in certain areas, not in other areas. So the distribution is very patchy. Now, what causes that? Okay? What causes that is interesting, and it's related to sediment. The different plants, they have different environmental tolerances, right? Just like organisms. There's some like, well, okay, if you go to the Lowe's and you buy some sort of a tropical house plant, and you know you can't put it outside because it's too cold for it. So if you buy a goldfish, you know you can't put the goldfish in a saltwater tank. So the same thing goes with these plants out here. They each have a range of environmental conditions that are best and optimal for their growing. So, the important things are, some of the important parameters are how much salt water can they handle, right? They have, these are called halophytes, so they love salt. They can handle salt. They have mechanisms in their biology and their systems that enable them to handle salt. But how much salt? How much, right? And then also how much flooding can they handle? If you take a plant, imagine the tide going up and down. Sometimes these plants are covered in water for hours upon hours upon hours, right? So how much of that flooding and waterlogging can they handle, right? So just two examples of parameters that are very important to these plants. Now, so why do we have Spartina patens here in the interior and alterniflora out along the edge, and then the sinusoides right on the bank? Is because underneath all the grass there is differences in topography, right? Small differences in elevation, and they're small enough that if you're walking and not thinking about it, you might not notice. We're talking no more than a foot, less than a foot usually. Very small differences, and that's actually can make a huge difference to the plants. Just a few inches higher in elevation, and a plant that's there is going to be flooded a little bit less than the plants that are at a slightly lower elevation. They will get a little bit less salt water. They'll get greater exposure to fresh water from the rain. And so these small differences in topography of the marsh have an effect on which plants are able to grow where. And that also explains why we have this invasive all the way in the center, right? So the Phragmites really likes fresh water, and it'll grow on these higher grounds. Spartina patens is what we refer to as a high marsh plant. It grows at a slightly higher elevation, and the alterniflora grows at a slightly lower elevation. Now, the sinusoides, you almost always see that right on the edge of the bank, because there's a natural levee. There's this a bank right on the edge of the creek, and that is slightly higher in elevation as well. Okay? So between these different parameters, environmental tolerances of the plants, combined with the topography of the salt marsh, we get different plants able to grow in different areas. Okay? Now, how do we get these elevation differences? There is two different things that are at play here. In the big picture, we have the ocean off to one side and land off to the other, and so there is a big spatial scale gradient from the ocean into the shore area and into the upland, freshwater trees and grass and lawns and things. So there is this large spatial scale slope to the land, and the salt marsh is going to be wherever that slope intersects with sea level. Okay? So we're going to have, so that's the one thing. So closer to land, the elevation gets higher, and closer to the ocean, the elevation gets lower. That's the big spatial scale. And then in terms of the smaller spatial scale, like on the order of this area, there is control on a smaller scale based upon the sediment and how much sediment deposits where, and also what are the plants doing? The plants, their roots, right? So what happens when we get, every time the tide goes up, right? The tide goes up and the tide goes down. When the tide goes up, the sediment, or the tide also is going inland, right? So tide goes up, tide also goes inland. And so we have the horizontal movement of the tide corresponds to the vertical movement of the tide. So when tide goes up, the land is flooded, then what happens is the water gets all on the marsh. Okay? Water gets on the marsh. Now, what is in the water? There's sediment in the water. Okay, so the sediment that is under these plants is gets here every time that there is a flood tide. So the water gets up on the marsh, the sediment gets in on the marsh with it. So, part one. Part two is the sediment starts to settle out. Now, sediment comes in multiple sizes. Geologists will talk about clay-sized particles, which are ultra small, silt-sized particles, which are a little bit bigger, and then sand-sized particles. Okay, sand-sized particles are between 2 millimeters and 63 micrometers. Okay, but a lot of what gets up onto the salt marsh is on those really fine silt and clay-sized particles. Nevertheless, even though they're very small, there is still a large variability in their size, and that size is part of what determines how quickly it takes them to settle to the bottom. So they get up onto the marsh in suspension, and then they start to settle to the bottom. Why? Partly because the plants slow down the water flow. Okay? Faster water can carry larger particles, slower water carries smaller particles. So the water in the creek gets up onto the marsh, slows down, it loses its capacity to carry sediment. So the sediment starts to settle out. And where do the biggest particles are probably the heaviest, and so they settle out first. So we get a pile of the largest particles right on the edge of the creek. Right? And then as the flood continues into the marsh, the next largest particles will settle out, and then further in, the next smallest, and then the next smallest, and way in the center of the marsh, farthest away, the only sediment that's left is the really fine stuff. Right? So a pile of larger particles is taller than a pile of smaller particles. So what we end up with is, right on the edge of the tidal creek, a bank, a natural levee, and then it dips down, and we have a section of a low marsh, which is low in elevation. And then the further away we get, we are going up the gradient on toward upland, number one. So there's less flooding up there. It's higher in the tide range. There's less flooding, and also the sediment that gets up there is finer. So the way that sediment behaves in water, and the way that what the water does when it gets onto the salt marsh, is another control on the elevation. That explains the banks and some of these other smaller scale areas of topography. Now the other thing to remember is that the plants are also growing underground. We have the below ground biomass, which is basically the roots. So the roots of the plants actually add, as they grow, the roots of the plants growing can add a little bit of elevation, right? So that's kind of neat. The plants help, so they help by slowing down the water, they help by growing their roots, and all of last year's dead biomass, this is going to, if we dig down in here, it's starting to decay, and this last year's biomass will decay over time and become part of the sediment, all right? And that's another way that it helps. The third way that the plants help is by protecting that sediment. That sediment down there underneath the Spartina patens is protected very well. And it's less likely to get resuspended. Are y'all good so far? No questions yet. All right, cool. So, tide goes up, water floods the marsh, water slows down, sediment settles out. Okay. Now, the tide is going to go back. So the sediment that just got settled, it might pick up and go back. Also, imagine what happens if it rains. If it rains right now, the rain can, or wind, or just about anything, can resuspend sediment as well. So we have sediment that deposits, and then we have a period of we can have erosion. So the sediment can erode as well. So over time, if you imagine deposit and then erode some, and then deposit more and then erode some, and then deposit and then erode. If you take that process and you average it over a year, 100 years, 1,000 years, 1 million years, whatever, you average it over this longer time scales, you will have what's known as an accumulation rate. Okay, so deposition minus erosion equals accumulation. So the sediment accumulation rate in the salt marsh is going to be the product or the sum of all of those depositions minus all of the erosions over time. Now, it turns out to be a relatively low number, and interestingly, if you measure the sediment that deposited today and you multiply it times however many tides per year times however many years you care about, you're going to get a number that is different from if you measure the average accumulation rate by a different method, right? So let's say you use radiometric dating, you use lead-210 analysis, and you get the sediment accumulation rate over about 100 years, you are going to get a different answer than if you simply multiplied up today's sediment deposition. And again, that's because as you increase the time scale that you're averaging over, you also, you're having more episodes of deposition, but you're also having a greater number of episodes of erosion. Okay? So the whole deposition erosion situation is a very critical part of the salt marsh, but it's not entirely additive. And also, now I don't understand this part as well as the physics because I'm not a biology person, but the plants themselves can, if I understand correctly, they can exert a little bit of control on their local elevation up to a certain amount. So the way that the plants interact with the water and the amount of flooding and their environment can have an effect on this as well. And why is this important? It's important to think about controls on salt marsh sedimentation, controls on salt marsh elevation, because if we want the salt marsh to stay put, if we want to have salt marshes to enjoy, to provide nurseries for baby fish, to buffer storm surge and things like that, then it needs to exist. And the salt marsh can only exist if it remains between your average high tide and your average low tide. So there's a very narrow window. All right. So what I want to do, I was out here yesterday with Liz, and we planted something. Right? One thing about marsh science, at least the sediment part, right? What I do is a lot of physics. And this is really, for me, it's all physics-based. You can look at the same sediment. You can look at all this sediment from a chemistry perspective or a biology perspective, but I do the physics. And the cool thing is that you can do this with extremely low-tech stuff. All right? I put down yesterday a tile. All right? This little tile here, it was clean, perfectly clean yesterday. This is a ceramic tile. I got a box of 25 of these or 50 of these at Home Depot. I get a lot of my science equipment from Home Depot, actually. So this tile, I put it down yesterday at about noon, and so it's been here for 24 hours. Okay? Now there is a little tidal creek here, a very short one. This larger tidal creek connects to an estuary, which connects to the ocean, and then this little inlet here, it comes up, snakes its way under the grass, and lets out right here. Right? So the water, when the water floods onto the marsh, oftentimes it comes up through the tidal creek and then spreads out in the interior. And so then, if you can see, if you look past the grass, right, there's lots of all this dead grass and stuff, but there is also little bits of brown sediment stuck to this tile. And maybe if I move some of the grass, maybe. Okay, so all of this little brown stuff that's not grass pieces, that's sediment. And that sediment was deposited, it's accumulated sediment, at least for the time being. This sediment has survived being deposited and being eroded, right? And so that's sediment that was deposited right there, okay? So, low-tech science, right? Now, what I might do is put this out and collect it 2 weeks from now, right? Or a month from now. Or I could put 3 in a row and collect one tomorrow, put 4 or 5 of these in a row, collect them on different time scales. And so over multiple days, multiple flood tides, sediment will be deposited and then eroded, deposited and then eroded, and then I'll have a record of it here. And then I can pick up the tile and scrape it off and take it back to the lab and do whatever I want with it, right? And do further analyses. So that, all right, sediment accumulation, really, really low-tech science. So, and now if we think about what else happens. Sediment is deposited, and the plants live and they die. So we have sediment depositing and eroding. Plants are living and dying. Organisms, there's a wide variety of organisms living here. And then what happens, right? So at the end of the season, these plants will die, or at least the above ground will die. As we saw when I parted the patents for you, there is sediment, the decaying above ground biomass is going to join the sediment, right? One of the hallmarks of marsh sediment is that it's highly organic, and a lot of that organic matter comes from the above ground biomass, also comes from the below ground biomass, right? So whereas if you're imagining this in your head and you're imagining sediment depositing every time there's a high tide, you might think layers. Well, but layers only happen if there's no other biology, no critters, no flora, no fauna, no nothing, and there's no water flow. So we do not actually get much like fine scale layering. What we do get is roots with mud all around. Right? So what I want to do now is to try to pull up a core, a short core, and if I can't get a core, then I've got to shovel and dig. So I want to show you what is actually under all of this grass, right? Other than just sediment, right? Because there is some really cool stuff going on underneath the sediment. And I am going to start doing this. Hopefully we can get a core. So, what I've got here, this lovely device, these edges are kind of sharp. So what I can do is put this in and turn it around, pull it back up again. Hopefully the sediment inside the barrel comes up. That would be nice. Doesn't always happen that way. So, wait. Oh, come on. Oh, very thick root mass. There we go. Very thick root mass. Okay. So now, turn this around. Okay. So now there is sediment inside. Question is whether it'll come up. You see, there's water. All right. If there's water in the tidal creek, and the water is this far below the marsh, which it is, where's the water table? The water table is really, really, really close. It might be, sometimes the water table is just right at the surface. So all that water down there creates some suction. So sometimes these don't come up very easily because of suction. But we shall see how much I can get. No, you know what? What did I just say? Rock it back and forth a little. Oh, come on. Nuts. All right. Let's try a little bit further in. doesn't work, I should probably just dig a hole next. Nope. Ah. That's annoying. Well, we could try one more. Well, what worked last time? We were over there last time. Let's go in. Out here just a little more. Change position. Concerned that that thick root mass. Let's see. What we should have done is what I considered yesterday. Instead of digging a hole yesterday. Oh well. It is what it is. We'll make the best of it. Nope. Alright, fine. Let me instead dig you. I'm just going to dig you out a little shovelful. Alright. Let's see. Get this started with a knife. And what I'm trying to show, my goal is to show you the root mass and stuff. It changes in color. Alright, it's another cool thing about this marsh sediment. It's not all the same color as you go down. And that's because of some chemistry stuff associated with hold on. Chemical reactions associated with all the water logging. As cool of a core as I had intended to get you, but because it's not really a core. But what I do have here is the top section of the marsh here. Okay, so what we're looking at is the first several inches. All right, there we go. So this is the grass, the marsh surface here, and this is what we see. So what is in, a lot of times what you'll see is a dark brown layer at the surface, a lot of times, not always. And then what you see is some variation on gray as you get further down, right? And so that's thing number one, differences in color. And the gray sediment is indicative of low to no oxygen, right? We've all seen rust. Rust is oxidized iron. But if there's no oxygen, then any iron present in the sediment is going to become reduced, and reduced iron is black. Okay, so there's that. Number two, there's organic matter tends to decay into a dark color, and there's a lot of organic matter in here. We have a lot of roots, right? So there are roots from, like active roots from today's plants, and there's also gnats, more gnats than I can shake a stick at, and then there's also old roots from previous years, and as you go further and further down, if we were to dig and really dig, we would see down here, sooner or later, these we would see the roots get more and more decayed, and they would get more and more or they would get finer and finer. And over time, the roots, as they get buried by more sediment and newer plants grow on top of them, the root mass becomes more and more, it just decays into, non-specific, generalized organic matter. So if we go down far enough, we won't see roots anymore, right? But we will still see an organic rich mud. Right? So now the sediment in between, which is what I've got all over my hands here now, this is actually fairly brown and not very gray, but anyway, the sediment that I'm feeling, right, what this feels like to me is it feels very silky smooth, and that tells me something. The fact that it feels silky smooth to my fingers is like cold cream or like a mud mask or something like that. It feels that way because there's no sand in it, right? Sand-sized particles. Even though some sand sand can be very, very fine, nevertheless, to most humans can feel a little bit of grittiness when you are rubbing sand between your fingers, right? Now, silt and clay are not the same thing, right? Silt-sized particles are larger than clay-sized particles. Now, both of them are going to feel like they are smooth when you rub them between your fingers. Okay, but what I swear, this is a geologist thing, what you will see geologists do is to put a little bit of this mud, rub it on your teeth, and I swear, if it's silt and it's a little bit larger, you will feel it gritting against your teeth, right? You literally just do that, grit it between your teeth. Oh, sure enough, yes indeed. Pardon me while I spit. We do that. And why would you do that? You do that because if you have some reason why you want to know, you are in the field, you're taking notes, you just need a rough estimate. Is this silt or clay? Is there any silt in this? Is it all clay? What? So that's a little dirty geology trick for estimating particle size. All right, so I know that this is clay and silt and plant matter. Now, so what do you now? The word for silt plus clay is mud. If a geologist says mud, we specifically mean sediment where the mineral pieces are silt and clay size. And then when we add all of this root to it, right, now we have a sediment that we call peat, right? So the roots, the dead and decaying root matter, plant biomass, plus all of the mineral sediment, that together we call this peat. Now, in some parts of the world, they dig up ancient peat deposits. I remember a TV show about Scotland. This is burnable. In fact, I saw a marsh one time out on the west coast where there were signs expressly forbidding camping and campfires precisely because the marsh could be burned, and because peat can be burned. And given enough time and pressure, the peat could become a rock called lignite, and it could even then become a rock called coal, given time and pressure. So anyway, that is what we see under the surface. And geologists might be interested in that, and you can do all sorts of fun stuff. If you get a core, and it works, you can slice that core into little sections, and like 2 centimeter sections or 1 centimeter sections, and then you can run chemical tests, a variety of chemical tests on that sediment. You could, for example, you measure the amount of the activity of radioactive lead-210. It's a natural part of the environment. It's not dangerous in the natural environment. It decreases as you go down, right? So there's less radioactive activity of lead-210 as you go down, and the slope. So you plot that activity with depth, and you can figure out the sediment accumulation rate, the average rate, on timescales of about 100 years or so. So we could do that. We could also measure nutrient content, PCBs, some sort of pollutant. We could look for the pollen. We could look pollen. We could do all sorts of cool stuff. And what that does is we can combine this physics part of sediment, and we can see, have there been any changes in the sediment accumulation rate? We can see how old is the sediment at different depths, also see how whatever chemical stuff we measure, we can see, for example, did we start to have a particular chemical pollutant at a certain time? Have those have the amounts of chemicals getting into the marsh, has that changed over time? That's another thing. Pollen analysis, we can look to see how has the plant communities changed by looking at the fossilized pollen that they leave behind. So there's all sorts of cool stuff that we can do. And as mundane as it may seem, the simple physics of getting sediment out of the tidal creek onto the marsh and back again is actually a major part of the story and foundational to a lot of science that goes on in salt marshes. Now, is the time showing up on yours?
No.
I have to fish my phone out with dirty hands and say it is 12:36. Okay. So, has nobody written in with a question yet?
Just say hellos and highs, but no questions yet.
No questions. Well, that's okay. You know, we do not have a set time for this to last.
There's one question.
Oh, one question.
Do the cores come out easier on the slightly higher marsh rather than the low marsh where you've been attempting?
We tried the higher marsh yesterday and I didn't get anywhere. If I was taking a sediment core for not for demonstration purposes, but for study, I would use a different setup with suction. Right? It works better if you have a little bit of suction at the top, and that helps to break the suction at the bottom. So, but we can demonstrate, and maybe I'll get lucky. Maybe this will work better. I don't know.
Try that little black grass pocket. Maybe.
Oh, in the black grass? Yeah, because that's different. Let's try this. Yeah. You guys see how this color is different over here? It's a little bit darker in this circle. That's a different species of grass. Whew. Yeah. The hardest part about getting this up is the suction at the bottom of the core barrel. Now, I have been on coring expeditions before as a grad student where, grant funded, the government has given us money to do this, and none of the cores come up. We had to get shovels and dig these cores out, and they were 2 meters long. You can imagine how dirty we were. But sometimes you have to do that. So, oh, yes. Oh, excellent. We only got part of it. Thank you, whoever that was. All right. So now, here we can see, biomass, all right, above ground. Now, you can see, I hope you can see, that this is kind of gray down here. And it's gray because, again, water prevents oxygen from getting in there, so this is low to zero oxygen environment in here. Now, so that's why it's gray. We can't see the sediment-water interface very well because of the plants, but that's okay. This is very thick. Now, a person that knows what they're doing, a plant person with more plant knowledge, could get in here and tell you what all of these roots are. Okay, here it starts to, there we go. Okay, and right here it's getting more muddy, so we're getting progressively less plant matter, and this plant matter down here is softer, so there's getting less plant matter as we go down. It's getting softer because it's decaying. Now, in a low oxygen environment, organic matter decays a whole lot slower than it does, and so this will take quite a long time. Now down here, right about here, it changes color, so it's an even darker gray down here. And there's very little plant matter left in this. And probably what was down there was plain mud. Probably. Yeah. So yeah, good suggestion, whoever that was, because I was not going to try it up here because it didn't work yesterday.
It was Steve.
Yeah. Any other questions?
Let me double check. How do you know how old the sediment is? Lori Ann wants to know.
Okay, how do we know how old the sediment is? Well, this is where what I was saying about lead-210 analysis comes in. There's several different things you can do. Lead-210, cesium-137. So lead-210 is a product of the natural environment. You've got uranium in rocks as a natural part of the environment, and lead-210 is part of the decay chain. So if you have rocks, you might have lead-210. But anyway, that's cutting out a lot of detail. So there's that. Now, cesium-137 is also in these sediments. Now, the cesium is a much more entertaining story because that comes from above-ground nuclear testing. The students that I teach now are kind of horrified. They're in their 20s now. They're kind of horrified with the idea that we used to test nuclear weapons above ground. Well, yeah, we did that. So instead of seeing the highest radioactive activity at the surface and then decreasing as you go down, in that case, you see a peak below ground. And that peak approximately, that corresponds to approximately 1963. Yeah. The time when we had the largest number of above ground nuclear tests. If you live in the right area, there's a second peak higher up that corresponds to the Chernobyl nuclear power plant accident, okay, 1989, I think. And then other things that you can do. If you get a really long core, right? You get a long core, you go all the way down to the very bottom of the salt marsh, right? There's going to be sand and gravel down there where that used to be a beach or whatever, sea level goes down and erodes a lot, and then sea level comes back up again, right? So this marsh that we have is a product of the sea level rise since the last glacial maximum about 20,000 years ago. So there is a deep enough, you go deep enough, there's no marsh anymore. If you can get a sample of peat or some organic matter from that far down, then you can run a radiocarbon date on that. And radiocarbon dating is good for approximately 50,000 years, whereas lead-210 is only really good for, it'll give you an accumulation rate, and then from that you infer what year goes at what depth.
So Susan Green wants to know, do you ever use vibrocoring to collect your samples?
I have done that before. I have not at Stockton, but that is, yes, you can do that. And vibrocoring is, you imagine a metal core barrel. You can get really long, really like multiple meters. I think the longest one I've heard of, someone at Delaware was able to get 12-meter long cores. But it vibrates. You got a device that it's as simple as a cement mixer, right? If you're mixing cement, there is an engine, and then there's a metal thing you drop into the cement, and it vibrates the living daylights out of it, and it gets bubbles out of the cement. Well, if you clamp that vibrating thing onto a core, the core barrel vibrates, and it makes it slide down easier. And then if you lubricate the inside of the core, the inside of the barrel, and you apply some suction, you're probably going to recover a nice long core. But that is an option.
Susan Allen wants to know, when did you first get interested in studying sediments, marshes, and mud?
Right. So I went to Penn State University, and in between 1991 and 1994. So, and I'm the only active scientist in my family. And my ADHD was completely untreated, which I found I did not know at the time that it was not that I should have been on medication. So for one reason or another, my GPA was really low, and I didn't know that it was important to get an internship and things like that and summer jobs and all that. So for one thing or another, I was not well positioned to get a job in the field. And I didn't want to, I wanted to make more than minimum wage. So what I ended up doing was going off on a total sidetrack. I got into fast food management, and then retail management. I learned a lot of very valuable skills there, but eventually my hatred for the job overcame my fear of failure in grad school, and I said, I'm so sick of this, I have to try again. So then I said, I'm going to go to grad school. Now, me being religious, I prayed, of course, and I got in, yay, right? And they didn't care that my GPA was low and that my GREs were really low. My GREs were really old. They were high, but they were old. All right, and I liked Delaware. Delaware is small, which is attractive to a returning adult student. Delaware had a good reputation, and they had a coastal geology focus. So I saw that and I said, oh, coastal geology, that sounds awfully good. Because I really liked geology. Of all the sciences I had to take, I really liked geology. So let's do that. I'm getting bitten by things. My apologies. So that's, and while I was at Delaware, I took a course it was titled Coastal and Estuarine Geology. It was really all about sediment transport at the coast. And I fell in love with the complexity of the subject. Right? It's not simple. There's multiple mechanisms, multiple controlling factors, and the variables interact with each other as well. And it's a big complex network of web of complexity. And the more complex a subject is, the more I like it. And so that is how I got interested. And so then I decided at that point, I had succeeded well enough at graduate school that I knew that I could do, I was really confident in being able to do the PhD program. And I did, and I ended up working with that professor, Dr. Chris Summerfield, in my PhD program as well. And again, it's the complexity of the subject. It's inherently fascinating to me, right? Now, why did I tell you all the bad parts? Because I think I run into a lot of college students, my own students, who are really, really stressed out about, ruining their life. And it's really hard to ruin your life. You may have to take a different pathway than you intended. You may not be able to do exactly the thing you had in mind, but you could do something close. You don't have to go from your bachelor's to your master's to your PhD, postdoc 1, postdoc 2 professor. You can go off on a total sidetrack, do something unrelated, and get back on again. You can do that. You just might be hard to figure out why right now? Can we go this way?
Yeah.
Ay.
Whew. Oh, well, one last question. Steve wants to know, does coastal flooding increase sedimentation rates on the marsh, or does it tend to wash it away?
See, it kind of depends on the velocity of the water. Right? Faster water can erode, that's simplifying. It depends on the details about what happens. Among the important considerations is, this is not helping.
We lost our breeze.
Oh, is that what happened?
Yes.
So, what we tend to get, the velocity of the water, how fast is the water moving over the marsh? That's a primary controlling factor, both in terms of erosion, how much sediment might get eroded, whether any of these plants might get eroded, right? How much plant do you have? Because the plants are protective. The plants slow down the velocity, and they also, the root mat, or the grass mat on top, also protects the sediment that's underneath it. And could you come over here and show them how many of these little guys I've got on me? This is, I don't think they're biting me, but they're like touching me.
Well, we should wrap it up then.
We should probably wrap it up. And anyway, so on salt marshes though, a storm like a nor'easter that really erodes into the barrier islands. Most of the studies research studies that have involved nor'easters have shown that what happens with a nor'easter, because of the set of the grass, the grass is there slowing down the flow. The flow is shallow to begin with, which slows down the flow. Allows more sediment to drop out, and nor'easters can actually be depositional on the marsh surface, at least as far as the storm itself. So I am inclined to say, depending on what type of storm and what the details are, and what happens to the vegetation, it's more likely to be depositional. But that's not a guarantee.
All right.
Ooh. Anything else?
That's it.
All right. Thank you, everybody, for your time and attention. Now, if I understand correctly, this whole thing will be saved, and I think we're posting them on Stockton's website for later, number one. Number two, if you want to hear about something other than sediment, mud, and stuff, next week we are having another one. So it's scheduled tentatively, presuming everything goes right, for like tides and stuff, scheduled for June 8th at noon. And we will be hearing Dr. Christine Thompson from the Marine Sciences program. She's going to be talking about oyster restoration in Barnegat Bay. So, same bat time, same bat channel, tomorrow, next week, and it's biology this time. So thank you very much. Get on our Facebook page and like this. Talk to us. We like to talk to people. Thank you, everybody, and have a good day. Oh.